This is Math 26, section 2.3. 2.3. What is this section all about? It's all about one theorem. So we're going to spend the whole time talking about theorem. And this theorem is related to inverse matrices. And the section titled Characterizations of Invertible Matrices. But to do this, we need to recall a lot of stuff from previous sections. So the first part is this: a set of vectors, call them v1, v2, all the way to vk, is linearly independent and I'm going to write Li, linearly independent, if the vector equation x1 v1 plus x2 v2 plus plus xk vk equals 0 has only the trivial solution. X1 equals x2 equals equals xk equals 0. In other words, we say linearly independent if no vector in the set can be expressed as a linear combination of the other vectors in the set. So this was a definition of linearly independence. If you guys remember, was way back. That's what linearly independence means. If no vector in the set can be expressed as a linear combination. Linear combination means you can write one vector as, let's say, like v1 is 2v2 plus 3v3. You know, that's then linearly dependent. So the trivial solution means only when all these coefficients x1 to xk are all zeros. So that's one thing I wanted to recall. Another thing is, what does it mean to say A, matrix A is invertible? Do you guys remember? What is it from last time? So a matrix is invertible if what? The determinant is not 0, right? Determinant is not 0. And at the same time, if it's invertible, implies this arrow means in mathematics implies. Okay, implies it has an inverse. A to the -1 means inverse exists. So this means the inverse of A. It's a notation. Inverse of A. Another good thing to know, if A is invertible, then A transpose. Do you remember what A transpose? A transpose, when you make rows columns, columns rows, you got A transpose. A transpose is also invertible. We had people ask about square matrices. What do you mean by square matrices? Square matrices are those, the n by n matrices. They have the same number of rows and columns, like 2 by 2, 3 by 3, 1 by 1, 20 by 20. Those are called square matrices. Okay, those are all a lot of things I wanted to recall. What does it mean, the columns of A, of matrix A? are linearly independent. What does that mean? So columns of A are linearly independent if and only if and only if A has a pivot in each column. You guys know what that means? A has a pivot in each column. Can someone give us an example? Okay, so someone shared this answer with us. 1 0 0 0, then 0 1 0 0 0 0 1 0. That's the identity matrix. This has a pivot in each so the pivot is the first one you hit when you travel from left to right. The first number you hit, non-zero number. Those are pivots. 1 1 1 1. Someone is asking, do the pivots have to be ones? What do you guys think? Please share answers. No. Yeah, they don't have to be ones. They can be any non-zero numbers. Okay, so that's good that we recalled all this stuff about the columns. So how about if we have, how about this? 2 3 1 4 8 negative 1 4 0 0 0 0 0. This is an example of matrix A. What do you think about this matrix? Are the columns of A linearly independent? Are the columns of A are linearly independent? Li means linearly independent. Are the columns linearly independent?
No, because there's a zero vector.
There's the zero vector, yeah. Are they linearly independent? No, they are. The columns are linearly dependent because of the zero column. Good to keep in mind. Another thing, recall the one-to-one transformations from before. So if we have T maps V into W, let's say, we say this is one-to-one. So 1 minus 1 or 1-1 means one-to-one. One-to-one if T maps distinct vectors in V to distinct vectors in W. So in other words, two different inputs have two different outputs, the function language. Also, if the range of T is W, then T is called onto. So in other words, if you take any vector in W, there is a vector. There is a vector in V is going to get mapped to it. You will find a vector in V that is going to get mapped to that vector in W. And I'm going to show you very simple examples using mappings for now. And then you can tell me if this is good or not. So I'm gonna select first example that talks about, let's say we have, the first one is V and the other one W, and this is T here that maps this. So let's say this element get mapped to this element get mapped to this, and this element get mapped to this. So this is one-to-one because every distinct element get mapped to a distinct element in the other one. And it's onto. Because every element in W had a vector in or element in V that was mapped to it. Let me show a different example. Let's say we have 3 here. I don't know, let's say 6. Again, V, W, and T. Say this get mapped to this. This get mapped to this. This get mapped to this. Is this one-to-one? Well, the answer is yes. Every element in V get mapped to a distinct element in W. So this is one-to-one. How about onto? Is it onto? Well, but we say it is not onto. Why? Since some elements like this one or this one, those elements have no elements in V that map to them. No elements in V that get mapped to them. So this is not onto. How about a different example? Last example here. So say VW, this element get mapped to this element get mapped here, and this get mapped here. This one, notice 2 distinct elements get mapped to only one element. So this is not one-to-one, but it is onto. So if you haven't seen this before, came across this before, that was several sections back, then now it helps to see it. So now we're gonna go back up to the original theorem. It's all about, we call it the invertible matrix theorem, abbreviated with IMT. We mainly focus on the square matrices. So now you know what a square matrix is. So the theorem said if we have n by n matrix A, the following are equivalent. Means like if one of them works, then it just follows up with everything. So the first one says if A is invertible matrix, it's equivalent to say A is row equivalent to I sub n. What does that mean, row equivalent? Can someone give an idea or comment on this? Okay, so someone says the number of rows and columns are the same. Do you guys know what row equivalent means? Row equivalent
So
means, yeah,
like
go
the
ahead.
row operations transfer from A to IN.
Yes, so this means you can take any matrix A and perform some row operations to get it to become IN. Yeah, and someone is saying, so if you do some row operations and reduce it down to, or write it in reduced row echelon form, it would be the same as IN. So everyone okay what that means? The next one, A has n pivot positions. N pivot because it's n by n. So in each column there is a pivot number. Next one, the equation ax equals 0 has only the trivial solution. So the equation ax equals 0 has only the trivial solution. What does that mean? I want you to comment on this, please. What does it mean to say ax equals 0 has only the trivial solution? So thank you, Justin. So he's saying the only solution is x equals 0, 0, 0, 0 all the way. So he's saying this means the only solution is x equals 0, 0, 0, da, 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 0. Next, part E. The columns of A are linearly independent. The columns of A are linearly independent. So you know what that means now, right? The columns of A are linearly independent. The linear transformation T of x equal ax is 1 to 1. So now you know what 1 to 1 means. The equation ax equals b is consistent. You know what consistent means, right? Can someone remind us about this part, the consistency part? So at least it has at least one solution. Some people say no, non-zero row with a solution. So you don't get like one of the rows that has all zeros than some other number other than 0, right? So that's called consistent. Has either one solution or infinitely many solutions. It has no solutions, then it's inconsistent. How about the next part? What does it mean to say the columns of A span Rn? I need to see your comments, guys. Every vector in Rn can be written as a linear combination of the vectors of A. Yes. So the span means every vector in Rn can be written as a linear combination of the columns of A. Now you know what onto means. J, there is an n by n matrix C such that C times A is In. We will show you what that means. Also, there is an n by n matrix D such that AD is In. So it's kind of like from both sides. That's what this means. Next one, the matrix A transpose is invertible. The matrix A transpose is invertible. We're gonna go over the proving all this, but we don't have to prove it like A implies B, B implies C, C implies. We don't have to go in that order. We will go in an order that would make it easier for us to prove. Okay, we're gonna take them one at a time and see how we can move with this. The first thing we're gonna prove, if A is correct, means if A is invertible, we're gonna prove the first one that J is true, that there exists n by n matrix C such that CA equals In. Okay, so the first thing comes to mind, invertible means A inverse exists, right? A inverse exists means A inverse is the identity if you multiply them. So let's prove A implies J. So A is invertible means A inverse exists. That means A inverse A is In, right? In. Because when the inverse of a matrix exists, if you find it and you multiply them together from either end, if you do A inverse A or A inverse, you will always get the identity matrix. So A is invertible implies A inverse exists. So this means since it exists, then A inverse A is the identity. And I'm trying to prove J. Look at J. It says there's a matrix C such that CA equals In. In this case, the matrix C is A inverse. So CA is In. So that proves J. After J, we're going to prove D. After J, we're going to prove D. And then you can scroll up, see what is D. D says the equation AX equals 0 has only the trivial solutions. Okay, means the only solution is the zero thing, zero vector. So how do you prove that from J? So we have, suppose CA equals In, and we need to prove that AX equals 0 has only the trivial solution. How do you do that? We can let, if U is a solution to this matrix equation, AX equals 0, then it satisfies the equation. In other words, you can replace X with U. So you get AU equals 0. What can we do on both sides? Because I want to use this fact or this CA equals the identity. I can multiply both sides by C on the left side. And then by the properties of matrices, I can regroup the C times AU as CA times U equals, and 0 times the other matrix is 0 matrix, or 0 vector. So what do we get here? We get that CA, we know it's In by J. So In times U is 0, but the In is the identity, It's like multiplying 1 times x. It's going to stay x. So that's going to still give me u equals 0. So what I assumed here, it's given that ax, let's say, to prove ax equals 0 has the only trivial solution, is you assume any vector u is a solution and prove that that u is 0. And that's what we did. So to get to D, next one where we have to prove D implies C. Sometimes, I don't know if you remember in algebra, let's say you have this equation and x minus y plus z equals 3 or something. So to solve this equation, what happens is you can add them. So these cancel. So 2x plus 2z equals 8. Divide by 2 the entire equation. And then let's say z or x equals 4 minus z. Okay? Then if you put this back in here, substitute, you get 4 minus z. Oh, I don't want it to happen this way. Let me change this to 3 here. So that's 4, that's a 2, that's a 2z. So then x is 4 minus 2z plus y plus 3z equals 5. So you get 4 plus z, or just z plus y equals 1. So y is 1 minus z. So in this case, when you solve this system, you're going to say x is, I got x to be 4 minus 2z, and y is 1 minus z. How about z? Z equals z, right? So what do we call z in this case?
The free variable.
The free variable, right? That's the free variable. So now in the matrix or pivot stuff, what do we get for the free variable? So when we say the equation has only the trivial solution, means the 0, 0, 0, and so no free variables. So no free variables means you will not get something like this, where you have a variable that can take any value. Okay, so in this case, the matrix A has n pivot positions. We don't have any free variables. So in each column, we're gonna have what? A pivot number, right? In each column. So it proves itself. So that's what C, we wanted C. That's what C says. The next part, if you look back at the map, we started at A, we went to J, J to D, D to C, and now we're going to prove C to B. And then after that, we'll prove B implies A. So C to B, let's prove that, C to B. So what is C? C says matrix has n pivot positions. And what is B? B says A is row equivalent to IN. A is row equivalent to IN. So how do we connect these together? Row equivalent to IN.
Since it's like every column has a number that is non-zero, so
A
it's
pivot.
kind of, yeah, it has a pivot, so that way if you do like row operations, it's going to be becoming the numbers in the matrix A.
Becoming the number. Remember what it says. It says row equivalent to IN.
Oh, then the other way around. Like, if you have a pivot, that's a non-zero because it's non-zero, so you can just multiply the elementary by a number to become
1.
the. Yeah.
So So, and if A has n pivot position, it has a pivot in every row and every column, right? And what we can do, we can use some row operations to write it in reduced echelon form, which will be equivalent to in. If you remember how we what we defined as equivalency means. So the reduced echelon form of A is going to be in. If you remember, last week we were doing a problem, and then we got an answer. I thought I did something wrong before, but then we got a different answer, and then a student said, no, we can still go do some more operations and transform it into that in. Do you remember? One of you told me this, which we went over it last time, and we got the in. So again, if it has n pivot positions, this means there's a pivot in every row and every column that can be cleaned up using or the matrix can be written in the reduced echelon form of A to get us in. The next one, which is the last one in that cycle, we need to prove B implies A. Means the equivalency to in implies A is invertible. That's what A says. That matrix A is invertible. So let's see how we do this. If A is in row equivalent to in, how can we convince ourselves that this means A is invertible? Again, what is invertible? How can I prove a matrix is invertible?
If its determinant is non-zero.
Yeah, that determinant is non-zero. So if we got A to be written in equivalent to in, what is I here? I is the identity matrix. So what would be the determinant? Would the determinant be 0 or non-zero?
It would be
non-zero. Yeah, non-zero. Maybe I can show you some examples here about, let's say we have any matrix, let's say 2 or A, B, C, D. The determinant of this, if you remember, the determinant is AD minus BC, right? AD minus BC. That's how you find the determinant. So if you have a matrix, let's say 2, 0, 0, 4, like this, on the main diagonal, the entries are non-zero, but 0 everywhere else. Then the determinant would be simply the product of the diagonal entries, like the product of these entries. It's going to be 2 times 4 minus 0, which is 8. And this works the same if you have 3 by 3, 4 by 4. So the determinant is basically the product of all the entries on the main diagonal. And since it's an identity, those entries on the main diagonals are going to be 1s, right? So the determinant is going to be non-zero. So this means if A is in row equivalent to in, automatically the determinant is not 0, therefore A is invertible. I hope that explains it. So now we continue proving more of those. The next one, we're going to prove that A implies K. A implies K. What is K? Well, let's see. A is invertible, so we get used to it. But K says there is an n by n matrix D such that A times D equal in. Well, that should be easy. So for A to implies K. So A is invertible. This means the A inverse exists. Okay, A inverse exists. For A inverse to exist, This means A times A inverse is the identity. Again, you can also write A inverse A is the identity, but we want it to be in this form, A inverse. So then this A inverse is the matrix D, that you can replace that with matrix D. So you get AD equals, then we get AD equals the IN, and that's what we wanted to prove. The next one, we need to prove that K implies G. K implies G. What is G? If you go back, G says the equation AX equals B is consistent. Okay, so watch how we're going to prove this consistence. So we take any B in Rn, any vector B in Rn, then INB is B. This is like you're saying 1 times 2 is 2, but then we need it that way. We need it that way because I can use K, which says that IN equals AD, and replace IN with AD. So you get ADB equals B. Okay, I need to prove that is consistent. Then I can rewrite the ADB by grouping DB together, like so. But DB is just a vector with another vector. You're going to get another vector X. So you get AX equals B. So X equals DB is the only is a solution, or the only solution. So it's consistent. So we proved A implies K, K implies G. And now we need to prove G implies A. Means if AX equals B consistent, then A is invertible. Okay? So I want to prove G implies A. Okay? How do you prove that? Invertible, it's invertible. So assume G is true. This means the equation AX equals B or EI or whatever you want to call it has a solution. Call it UI, where I goes from 1 to N. Again, I want to prove it's invertible. So let's see what we get. Let D be the matrix whose columns are the UIs. So this means D can be written like this: U1, U2, UN, like that. Whose columns are the UIs. Then AD equals IN. And what does that tell us? If the D, you write the D this way, U1, U2, U3, all the way to UN, you can, in a way, rewrite it as it's AU1, AU2, AUN. It's kind of multiplication. But AU1 is from this equation here, it's E1, and the other one E2 all the way to EN. Since you're getting those E1 all the way to EN, that proves A is invertible. So do you know what E1 here means? E1. Recall E1 is 1, 0, da, 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 0. Do you guys remember that? E2 is 0, 1, all the way down to 0. and En is the last one, 0, 0 all the way to 1. So you're getting a matrix that is like an identity matrix. And you know that the determinant is not 0, therefore A is invertible. Next, it says here by previous sections, if you go back, we proved that G and H are equivalent, means this arrow means equivalent, means if G is true, H is true, and vice versa. Also, we proved that if H is true, I is true, and vice versa. We also proved, if you look back at the previous sections, D equivalent to E and E equivalent to F to be 1 to 1 and on to. And I highly recommend you go back and work them out and try to see how to prove G equivalent to H and H equivalent to I, and same thing with D, E, and F. And that will leave, so far we have all these are equivalent, A, B, C, D, J, K. See, there's no L here, I don't see L. G, H, I, E, F. So A, B, C, D, E, F, G, H, I, J, K. L is missing. L is missing. So we need to prove that A implies L or vice versa. A implies L. If A is the matrix invertible. L means the matrix transpose, A transpose is invertible. So let's see how to prove this. If A is invertible, then we need to prove A transpose is invertible. How do you do that? If A is invertible, automatically its transpose is invertible. So this is fine. But how do we go backwards? If A is invertible, then what can we prove A is invertible? Sometimes we'll put these theorems as true or false. Now, how do you prove this is invertible here? How do you prove A is invertible? Well, the way this works is we know that the transpose of A, the transpose of the transpose is A itself. Right? From last lecture. So if you have a matrix, let's say 1, 2, 3, 4, 5, 6, and you transpose it, what are you gonna get? You're gonna get 1, 2, 3, 4, 5, 6. If you transpose it again, it's gonna give you this back. So the transpose of the transpose is A back itself. So what we have here, first, if A is invertible, then A transpose is also invertible. That's an automatic result. And to prove if A transpose is invertible, how do you prove A is invertible? You transpose this matrix. Assume this matrix is B or something. If B is invertible, its transpose is invertible. But its transpose in this case is A. So that proves A is invertible. Some quick comment, very quick comment. If A and B are square matrices, and if AB is I, like A times B is the identity, then A and B are both invertible. With B is the inverse of A or vice versa. So very quick, someone asked, give us an example to see if this is invertible or not. So to check if a 2 by 2 matrix invertible, all we have to do is find the determinant, call it matrix B. The determinant is you multiply across the main diagonal minus the 6 by 6. So -4 times -9 minus 6 times 6, which is 0. So then B is not invertible. How about something like this? Is this 3 by 3 matrix invertible? Don't say the answer right away. Let everyone think for 1 minute. Okay, what do you guys think? Some people said no, it's not invertible.
No, because
yeah,
the column vectors aren't linearly independent.
The second column with all zeros, because that column contains all zeros, then the columns are linearly dependent, not independent. So it's not invertible. By which part of this theorem is it? Which one? A, B, C, D, E, which one? So which part am I using? E, yes, it is E. So we say, since one of the columns contains all zeros, then the columns are linearly dependent, so it's not invertible by E of the IMT theorem. Similarly, how about this? Is this invertible? And you need to go back to the parts of the theorem from A to L. Which one applies to this? If it's linearly dependent or if it's invertible or not.
Part C.
What's part C?
The pivot.
Oh, this one, yeah. Well, 1 minute. We'll talk about something else. So back to this example here. Hopefully everyone looked at it. So if you look at this matrix, this matrix has pivot positions, the ones that I circled, 1, 5, 2, and 10 has 4 pivot positions in the 4 by 4 matrix. So this means it is invertible by part C of the theorem. If you look back at part C, you will see it. So we say it has 4 pivot positions. By part C of the theorem, C is invertible. So the matrix C is invertible. Now, this matrix C, we call it an upper triangular matrix. See, if you do it this way, it's an upper triangular matrix. What happens? Why are we concerned about this? Well, because C is an upper triangular matrix, notice all the entries on the main diagonal are non-zeros here in this case. Then it is in echelon form. So C is row equivalent to I. C is equivalent to I. So you can rewrite this in equivalent to the identity IN, and hence invertible by the IMT. So all these upper triangular matrices will look like this shape that you see there. That's called upper triangular. And we also have lower triangular, where all the entries on the main diagonal and below are going to be non-zero, but anything above the main diagonal will be zeros. And the last comment, if we have n by n matrix A has 2 or more identical columns, then its columns are linearly dependent and implies not invertible. Not invertible. So you will notice in the next section, they can give you, let's say, 1, 2, 3, 4, 0, 3, negative 1, 1, 4, 1, 2, 3 again. So it has 2 identical columns. When you calculate the determinant, that would give us 0. Implies not invertible. So the idea here is to keep in mind in this section that all these things we discussed today in the theorem are all equivalent. Implies, what does that mean? It means, let me go back up here. Let's say someone say, hey, the matrix A is invertible. Then you can tell them that the columns of A should span Rn, which is part H. You should tell them, hey, this means there is an n by n matrix, let's call it C, so that C times A is In. You tell them that the columns of A are linearly independent. You tell them that the linear transformation T of x is Ax is onto. They all mean the same. All these are equivalent. Means if I know one of them holds, I can use the rest of them to solve a question or something like that. It's kind of difficult to memorize all of them, but when you apply them several times, you should be able to memorize them.